We have to discuss today about the hardware control unit and microprogram control unit. Basically, these units are used to generate the control signals. So when CPU execute an instruction, different control signals are required, and these control signals need to be generated properly so that execution can be done and the result can be obtained. So there are different approach that can be used to generate the control signals, and the most common two approach are hardware control approach and microprogram control approach. So in this video lecture, we have to discuss one by one. First, we have to discuss about the hardware control approach, and later we have to discuss about the microprogram control approach. Let's start with the hardware control approach. Before starting the hardware control approach, here uh, this 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 is the complete instruction execution. When CPU execute one instruction, the instruction it is a addition of two number, uh, adding register value R1 with the R2. Then this addition pass through several steps, and this 1, 2, 3 already we have discussed in the previous video lecture. And this example needs 6 steps. Each one is called what? Each one is called control steps. Whereas for performing addition by reading the content of R3, which hold the memory location, and to place that value in R1 takes more one extra step because we are performing one extra memory access operation. So it takes seven control steps. So objective for this one is telling that each instruction need some each instruction needs some control steps, and in each control steps we are performing we require some control signal to be generated properly. So for example, we need PC out first, and then we need MAR in, and we need read signal, and we need select for signal, add and Z in. All these control signal to be generated are this control step number one. So let's we have to discuss how these control signals are generated. And in the first approach, that is the hardware control approach. In hardware control approach, we are using different hardware circuits or combinational circuits by the help of logic gates to generate the control signals. Just what we have told, like PC out, MR in, read, write, all these things. Okay. So here instruction is placed in the IR. Instruction is placed in the IR, and instruction to be decoded by the help of a decoder, and this decoder is known as instruction decoder. And we are also using another decoder later in another diagram also, that is called control step decoder. uh, then these two decoder are helps. One is called control instruction decoder, which takes the input from IR, and one is called step decoder, which takes the input from control step counter. Combinedly put the information to encoder circuit. And encoder, by the help of this step decoder and instruction decoder and other external inputs and condition codes, then we generate the control signal. So the more detailed diagram by separating the encoder and decoder is shown here. In the next diagram I will describe, and the operation of each unit we have to discuss one by one. So in this hardware control basic block diagram, it shows different decoder. One is called instruction decoder. This is connected to IR, and one is called step decoder. It is connected to step counter. So the role of the control step counter is when we execute one instruction, it needs several steps. That is called control steps. So control step counter, the responsibility is to count the number of control steps required for a particular instruction. So if the control step, the maximum control step required for any instruction is n, then the number of bit required for a control step counter will be log n to the base 2. For example, if though we need a 8 number of control steps, then control step counter will be 3 bit. If we need for 16 number of control steps to execute one particular instruction, then the control step counter will be 4 bit. That is the relationship between the maximum number of control steps that is required, and the number of bit that to be in the control step counter. So the control step counter bit depend upon the maximum number of control steps that is required for the particular instruction. And this input from the control step counter is connected to a step decoder. For example, if we need the maximum number of control step is 16, then the control step counter will be 4 bit and step decoder will be 4 into 16 bit decoder. That means the input to the step decoder is 4 and the output is 16. And each step decoder will generate the signal for timing T0, T1 to T15 this way. If the step decoder is 3 into 8, then the timing signal will be generated as T0, T1 up to T7. That is the responsibility of the step decoder to generate the different control signals. Also, these control signals may vary from instruction to instruction. One instruction may take less number of control timing unit to generate the output, whereas another instruction may need more. But maximum we have taken here maximum means one instruction may be take 10, one other instruction may be take more than that or less than that. And the instruction decoder receive the input from the IR. Instruction register basically fetch the instruction from the memory by through the help of memory data register, and in that instruction some bit are represented as opcode, and specifically there may be that depend upon the instruction format, whether it is 3 bit is represent opcode or 4 bit represent opcode. If the instruction 3 bit is represent opcode, then the instruction decoder will also 3 into 2 to the 3 means 8 decoder. That means it input is 3 and output, one of the output is provided to 8 bit, and one of the output will be activated for a particular instruction. For example, if let's say instruction 2 is activated, let's say it is addition. This instruction say this, let's first one is represented as 000 and second bit is represented as 001. We interpret this as addition. So when this addition of code it received from the instruction register, then this addition needs several steps. If you take the example of the previous step, it requires 7 steps. So this addition to be performed for T0, for T1, for T2 up to T7 or T6. If it is 7 step, it have to go up to 6. So in each T signal, we have to generate certain control signals. In each timing unit, we have to generate some control signals. And once we reach to T6 and we generate the appropriate control signal, then we have to reset this timer to, we will start not to T7, we have to start from the T0. And this is for another instruction, let's say 000, or you may represent a subtract like this. It will continue up to like that. So the encoder circuit takes the input from the instruction decoder and step decoder for the timing unit, timing signals, and external inputs like your wait for memory function to complete and interrupt, and condition codes like branch instructions or jump instruction. This combine all these inputs from the encoder, combine all this input from the instruction decoder, step decoder, external inputs and condition codes. Then it generates the control signals. And this run and end are two different signals. When a control signal is T0 and it need more timing signal, then it it pass the information to the control step counter to increase. So it will come to T1 and T2, and when it is the signal is completed, it will pass the end signal so that it will start from T6 to T0. That is the role of the end and run signal. So this is the block diagram which represent the hardware control, where a clock is connected to control step counter. Clock responsibility is to generate clock signals, and this clock signal by the help of control step counter increase when the run signal is activated and reset when the end signal is activated. So now we have to discuss the unit of each block in hardware control unit. First, the control signals are generated by the taking the inputs from the all the blocks like control step counter, instruction decoder, condition codes, and external inputs. We have to start one by one. First, step counter and step decoder. Already, it is we discussed that step counter is required because we have to count the number of control steps required for a particular instruction. And the relationship is that if the n be the maximum number of control steps required for a particular instruction, then the uh, number of bit required for counter will be k, and k is nothing but your log n. For if n is 8, the value of k will be 3. For 9, the value of k will be 4. And depending upon the value of n, we have to generate the timing signals, and these are generated by the help of a decoder known as step decoder. And this encoder and decoder are responsible to generate the timing unit or timing signals. Then already there is a run and there is a end signal, and run is used when we have to increase the counter signal, and end is there when we have to end the signal, and when the control reaches to the maximum timing unit. I will come to these two signal later. Now instruction decoder. It is the instruction decoder. Instruction decoder role is to read the to take the input from the IR, and it will generate one of the signal to be activated, and other signal represented as INS1 to INSM to be disable. One of the signal, if you look at this diagram, one of the signal from this here to be enabled at a particular from a particular clock period to from another clock period, whereas other signal to be disabled. Suppose if you enable INS2, which is for performing addition, then this if it requires 7 clock cycle, then it will be enabled from T0 to T6. Whereas other signal like INS1 to INSM, they may be disabled. So once the INS2 is completed, next instruction may be another instruction for which another signal to be activated. This way, the instruction decoder enable a particular signal and disable other signals. And that is the role of what? That is the role of the instruction decoder is. And we are using different condition codes like conditional branch, conditional jump, subroutine call, and to detect the overflow. And they determine what type of condition code to be generated, and accordingly the signal to be different, and they play the important role for the determination of the control signals. So let's take one example. This is example already we have discussed. That is a performing addition between the performing addition by reading the content from a memory location whose address is placed in a register and placing the value in the another register. So here, if you mark, then you can find that we are getting the Z-in signal. We are recording Z-in signal in step number 1, and we are recording Z-in signal in step number 6. And we may record Z-in signal when a branch may be occurred. Okay. So this is represented like this. We are recording Z-in signal in the timing unit 1. We need that means at this timing unit we need Z-in signal. So Z-in activated in the when the timing is 1. In the same time, when the at timing 6, time unit 6, we need the Z signal along with add operation. So this way it is added with add operation, and signal is obtained. And in the same time, we may require Z for a branch signal in case of a branch instruction is executed. So this way a particular signal, say Z is generated at a different timing unit. That depend upon the instruction type of instruction we are using, and where the Z signal. So in this way we may get other signals like we are using Y in signal, or we are using wait for memory function to complete signal, or we are using MDR out signals. This way, hardware unit generates the control signal by the help of logic gates and combinational circuits. So from this diagram, it is clear that a particular signal Z in generated at T1 time, at T4 time, and at T6 time. So this is another example which summarize all this discussion through a simple diagram. Here instruction register is 16 bit, out of which this 12 bit is used for address for the operand, and this 3 bit is the used for what? This is used for opcode, and this one will represent the whether it is immediate or it is describe about whether what type of instruction it is. So all this information is provided to the control logic gates to provide to the control logic gates. This 12-bit address information, this opcode information through the instruction decoder 3 into 8 instruction decoder, and this instruction decoder is represented through signal like D0, D2 up to D7, and at a particular for a particular instruction one of the signal to be activated, and once this execution complete, then it will read another instruction, and accordingly to one of the signal by the help of instruction decoder to be activated. And this is the step counter where a clock is connected, and it has a clear and an increment button. So the clock is incremented when the particular instruction required more number of clock, and it is signal are generated as a T0 to T15 here, because the step decoder is 4. Step counter is 4 bit and step decoder is 4 into 16. That means the maximum number of control steps required for any instruction in this type of CPU is never be more than 16. So the instruction may be take less than that. So for instruction D0, it will initiate with T0 timing unit, timing signals. Then it will incremented when the incremented switch of the sequence control is activated, and this continue up to for example, if it is required 8 timing unit from T0 to T7, so this incrementer is enabled up to T7, and once it reaches T7 and the signal is generated, then the clear switch is enabled and increment is disabled, so it will reset to T0 for the next instruction, and that instruction will be selected by instruction decoder. This way, the control logic gets receive the input from the step decoder or instruction decoder for a particular instruction, let's say D7, and it generates the timing signals like T0, T1, T2 for that particular instructions, and depend upon the other type of external inputs and condition codes, it generates the appropriate control signals. This way, the hardware control circuits, hardware-based control-based approach works. And basically, it uses the logic gates, it uses the flip-flops, it uses the combinational circuits to generate the control signals, and it is faster because the performance of these gates is very fast in comparison to other approaches. So, hardware control approach is considered to be one of the fastest way to generate the control signals, and it is very commonly used by many processors, but in the same time the issue is it is difficult to modify, because if you want to modify your step decoder from 4 bit to 5 bit, it is not that much of easy. You have to replace everything. So it has restricted with this modification. I have to replace the entire hardware. That is the limitation for which the alternate approach is used, where the modification is required, and that is called microprogram control approach. However, hardware control based approach is very fast. Now coming to microprogram control approach is a approach in which binary control variables are stored in a memory. It is an alternative approach to hardware control approach, and in this approach different signals are generated by a program similar to machine language programs. We will discuss more detail about the microprogram control. Before that, let's discuss some keywords that is very frequently used and in the microprogram control unit. First one is called control word. Control word means is a typically a word in which each bit represents a particular signal, control signals. This is called control words. So this word length may be variable that depend upon the type of organization. If you are using a vertical microprogram organization, then the number of bit is more, and if you are using is less. If you are using vertical, then number of bit will be less. If you are using horizontal, the number of bit in the control word will be more. We will discuss the different vertical and horizontal based microprogram unit later. Uh, However, control signals represent a word where each bit has some meaning, and all these control words are kept in a memory that's known as control store. This is the control store, and basically the control store is nothing but a ROM. Control store is nothing but a ROM where all the control words are kept, and all these control words for a particular instructions are kept in a control memory. And for a particular instruction, all the sequence of the control words is known as a microrouting or micro instructions. If you remember that example you have taken where seven control steps are there, then there are seven micro routine, and each routine is represented through a control word. And where, for example, if we have to put PC out MR in, then the corresponding bit for PC out will be 1, and MR bit MR1 MR in bit will be 1, whereas all other bits those are not present required for that control step, which will be marked as 0. So this way a control word is represented, and all the control words are kept in the memory. It is not the main memory or RAM, it is a control store. Basically it is a ROM, and we have to read this control word by the help of a microprogram counter. This is a microprogram counter responsibility is to uh, read a particular control word or successive control word from the memory, so that signal will be generated by reading the control word. So we have to provide the starting address to the microprogram counter, so that particular control word once will be fetched from the control store, and it will be read and the appropriate signal will be generated. And once a particular control word is fetched and processed, then subsequent successive control word will be fetched by increasing the memory address. Suppose the first control word is placed in 300, the next control word will be available 301. This way the microprogram control units works. So in briefly, it is just by reading the content of a particular word, and to control unit generate the appropriate control signal by reading that control word. That means we are not requiring any hardware to generate these control signals. We just need at which time we have to perform which task. Suppose at first control word has identified that your PC out signal to be enable, your MR in signal to be enable, your read operation to be enable, your select for operation to be enable, your Z in signal to be enabled. So all this signal to be enabled in the first control word, and all remaining other signal to be disabled. That means by only reading the content of the control word, I can able to generate the appropriate control signal. This is the block diagram for microprogram control unit where instruction is fetched and the instruction is available at IR. Already the number of bit represented by IR already we have discussed during the hardware control unit, and we generate or find the starting address, and once we get the starting address from the IR, then the micro PC which need the starting address, and accordingly it will fetch the control word from the control store. Control store means the memory where all the control words, and these control words, for example, we are using I1, and in I1 we have control word 1, we have control word 2, we have control word like that. we have control word 7. So in the for I2 we have some control word. So starting address here is, let's say, 300, and the cost of starting address is 400. So for instruction 1 I have to fetch the starting address. I have to provide the starting address as 300, and the micro PC will retrieve the control word, corresponding control word, from the location 300. And once a particular instruction control word is fetched, it receive and increment that next address and receive the next control word from 301, and so on till it continue, till it reaches at the 307. So last control word for instruction 1 is available at 307. Once this control word is fetched, then it will read the next instruction, and that instruction, let's say, starting address is 400. So it will read from the 400 control word 401, like that. So this way the microprogram control unit read the control word from the control stores, and then the signal are generated by the help of a control unit. Also, we are handling with the external inputs and condition code as it is like your hardware control units. So in microprogram control unit, the control signal is generated by reading the contents of the CW control word, and control word are kept in a memory called control store. Successive control words for a particular instructions are load successive location in the control store. And also we can have different condition. Based upon that, we can able to the different condition like branch can be occur, subroutine call can be occur, and accordingly the control word address will be changed and it will be fetched accordingly. So this identify which action to be done first, which action to be done next. So in microprogram control unit, an initial address is loaded into the control address register. This address is usually the address of the first micro instruction that activates the instruction fetch routine. The fetch routine may be sequenced by the incrementing the control address register through the rest of the micro instruction. That means you have to first read the initial address, and once you read the initial address, then you have to provide that initial address to micro PC, micro program counter, and this stage is about the microprogram counter. Here it is known as control address register. And in once control address register receive that address, then it will retrieve information from the control memory or central store. We may refer it as central store. Once the information is available from central store, then we have to search for the data for the corresponding instruction from the control data register. And data may be available in different ways that depend upon the type of addressing mode. It may be indexed, it may be register based, it may be auto increment, decrement. Depending upon the data, then we have to obtain the data, and accordingly the control signal will be generated based upon the content of the starting address generation and content of the data register. This is the overall description how the control microprogram control approach works, and how the instructions signals are generated. Now we have to discuss the implementation part, how the control word contents are vary for horizontal approach and vertical approach. In horizontal approach, each bit of the control word represents the particular signal, and if you mark all this control signal, and if you put in a single control word, and then the number of bit may be more than 60. Here it is 16 plus 8 plus 8. If you consider all the combination, this is 4 plus 3. There may be more than 16 number of bits required in the control word. There may be 16 number of bits. So and first bit, if it is PC1, if it is your first control step is required PC in. If it is required, then you have to put 1. If it is not required, you have to put 0. Let's say the next bit is PC out. So PC out is there, so you have to push 1. So out of this 60 bit, only your 4-5 bits are using. In case of which approach? In case of horizontal approach. So in horizontal approach, the length of the control word is large because the number of bits is more, and we need a larger control store or a control memory to keep all these control words. That is the limitation. That means, first of all, we have to read a large control unit, large control words with large number of bit size, and we have to store all these control words in the memory control store. So this is the issue associated with the horizontal approach. So one of the approach is that those operations, they are mutual exclusive operations. Like if one signal is generated, then chance of generation of other signal is less or it is not there. We can put them in together in a group. For example, you may say that a read operation in memory. If we are performing a read operation, then we are not performing the write operation simultaneously. So read and write we cannot do in the same time. Like for in a memory ALU operation, suppose we are performing addition, then we are not performing subtraction or any other operation at the same time. So this type of signal can be grouped together, so that number of bits that is represented in horizontal approach, which is more than 60 or 70 number of bits, may be represented through less. So one typical example and this type of approach is known as vertical organization of microprogram control approach. So one of the approach explanation about the grouping is given here through uh, 1 to 8 groups. So this F1 is represented through 4 bits, where the 0000 represented no operation, 001 is represented as PC out. So when the first 4 bit is 001, it indicates PC out. Like 0010 MDR out, 0011 Z out. Like that, second group represented through 3 bits, where 000 is no transfer and 001 is PC in. So, and 010 is IR in. These are the signals, they are represented through 3 bits. And then third group is represented through 3 bits, where 00 is no transfer and 001 is MR in and 010 is MDR out. Like that. And these are the for ALU operation represented through 4 bits, and this is for read and write, that is represented in through 2 bits, and these are the select Y. When select 4, we in step number 1 we have to press that bit to 1, and when we have to select 0, that will be 0. And for memory operation, that is through 7th group, and continue and end for the increasing the timing signal from T0 to T1 at the 8th group. So in vertical organization, we may need a 4 plus 3, 7 plus 3, 10, 14, 16 plus 3, 19, 19 bits in total. 19 bits to represent all the signals. Represent all the signals. In comparison to the horizontal base approach, where we are using around 60 to 70 number of bits. So vertical organization is superior in comparison to number of bits required to represent a control word, and the number of control word that required less space in the control store. But the problem is for this encoding and decoding purpose, means which bit, which block, which bit represented for which purpose, that takes some time. So it is slower in comparison to horizontal approach, but it is take less space. This is the pros and cons of the horizontal as well as vertical organization. But most of the microprogram control approach, they supported, they prefer vertical organization, like the way it is shown in this diagram. So this way vertical organization is implemented by the help of groups, where each group represents certain control signals. For example, if a particular signal is represented like say 0001, and then it is then it may be 011, 011, then maybe 001. So that means this 4 bit represented is my PC out, and this 3 bit represented as 011, which one, Z in, and this 001 here it is represented as MR in. So this way the interpretation is done for in case of vertical organization. Now coming to an example, we have to show how the different control words are, how the different way to execute on a particular example, where uh, we have to get the operand in different ways. So this is the example where there is the operand can be available. This is a addition operation between uh, the instructions like this: add, source, and destination. But this source and destination, this address part, basically depend upon how you are getting the operand. So here operand can be available depending upon the addressing mode. It is indexed, or it may be auto decrement, or it may be auto increment, or it may be register indirect. So this four way for this example, it is available. So based upon the operand or operand address, or you can say addressing mode, the instruction to be generated, and the microprogram control have to generate the signal, or have to read the particular um, CW values, uh, that depend upon the addressing type. For example, if it is indexed mode, the it will read the contents of the it will read the content of the it read the control word from the location 141, 161. So the successive control word will be placed will be fetched from location 162, 63, and so on. So a branch instruction will be occur when the addressing will be indexed. So in the same way, if it is auto decrement, it will fetch the control word from the location 141, and successive control words will be fetched from the successive locations. For auto increment, the control word will be fetched from the location 121, and for auto register indirect, it will fetch from the 111. So this is a typical example to understood how the operand plays, the type of operands used in the instruction plays an important role for generating the different control signals by reading the content of the different location from the control store. This way it is complex, and in the same time, if you include or increase more number of addressing mode, then you have to update your control store. In this example, a particular instruction